I want to start off with just a brief introduction. My name is on the board. I'm Henry Robinson. I'm a software engineer at Cloudera, and I've been here for about 2 years. In previous lives, I worked on Apache Flume, which is now an incubator project, and I'm also a PMC member for Apache Zookeeper. But my day-to-day job most recently has been building monitoring tools and management infrastructure for Hadoop clusters for our customers at Cloudera. And it's in that context that I want to talk to you today. I want to say something about why managing Apache Hadoop is a hard problem, why I think there are some fundamental challenges that make it different from monitoring your database systems or your web server systems, and why the solutions should be software-based, but also should be based around collaboration between a number of different interested parties. So let me just page through my agenda. So the first thing I want to talk about is, what's difficult about making Apache Hadoop operational at scale? Oops, sorry, I'm getting used to this keyboard. Then the next thing I want to do is to talk through 4 brief use cases for motivating better operational tools for Hadoop. And those will be the management of the cluster in terms of managing service lifecycle, understanding cause and effect in terms of problem diagnosis, capacity planning in terms of figuring out if my cluster is big enough, and recognizing abnormal behavior. If you have a user who calls and says, hey, my job is running slow, how much attention should you really pay to them? So diving right in. So what's difficult about Hadoop monitoring? A Hadoop cluster is no longer really just a Hadoop cluster. It's a seriously complicated beast composed of a huge number of different interacting, complexly related actors. I've enumerated a few of them here, but there are more. If you've got a cluster of 25 to 500 to 1,000 nodes, each of those could be running several different processes. It's no longer just about Hadoop, as we all know. It's about Hive, it's about Flume, it's about Zookeeper, it's about HBase, it's about HDFS. All of these complex systems interact, but are loosely coupled. They're developed by often disparate communities. They're not necessarily built to make themselves easy to manage as one cohesive entity. This is a problem. All of these things are going to be producing a huge quantity of data, a huge quantity of monitoring data and metric data that we can use to identify problems, to predict problems in the future. But there's so much of it that recognizing the signal from the noise is a much, much harder problem than a couple of single metrics that you can maybe use to identify problems with your MySQL database, for example. This is what I posit is the fundamental challenge about Hadoop monitoring. So much data, so little insight. So, a thesis. We need, well, I suppose a manifesto. We need to reduce the operational complexity of Hadoop. Okay, great. There's nothing particularly controversial about that. We've all been saying that for a while. I'm going to talk about, in this talk, a little bit about how software should be able to help us with that. One thing you can do, if software is not the answer, is to hire an outstanding ops team. And if you are lucky enough to find one, congratulations, hold on to them, pay them a lot of money. On the other hand, it's not always possible to find great ops people. It's not always easy to find people who have deep understanding of all these different systems. They're changing, they're evolving rapidly. Software should help. So what's good operations software really about? Well, in this talk, I want to really say that good ops software is about 2 complementary motivations. One, management tools. As I said, lifecycle management, upgrade, provisioning, adding an extra data node. Is that easy to do? Is that hard? Monitoring tools, getting information back from your cluster, getting more data to the user so that they can make informed decisions. But as I said, you've got to filter it. One of my arguments is going to be that these cannot be developed as separate entities. You need to have a tightly coupled, explicit feedback mechanism between both management and monitoring for them to be effective for systems at this scale. So that really leads me on to my next point. Don't we already have good monitoring tools? And the answer is absolutely and unequivocally yes, but they're not good enough. Nagios and Ganglia and all the other tools that people are experts with are fabulous for the roles that they play. There's a huge amount of value in familiarity. But can you imagine, if you're familiar with Ganglia, a dashboard that has, for example, the disk drive I/O latency for every single drive in your 500-node Hadoop cluster? It would be about this big, and each graph would be about 2 inches wide. It would be ridiculous. You couldn't make sense of it. Domain knowledge is tremendously important here in aggregating this data and presenting it in a hierarchical, kind of drill-downable way that's easy to understand. So I don't want to marginalize existing tools. They're tremendously important. We must integrate with them if we're to be effective, both in penetrating existing operational systems and best practices, but at the same time, we can't rely on them. They weren't built with systems of Hadoop's size and complexity in mind. Excuse me. So with that in mind, I want to delve into the first of my kind of 4 quote-unquote use cases, and that's management of a Hadoop cluster, which is a tremendously vague term, I appreciate. As the number of distinct systems increase, configuration complexity is enormous. You know, I now have, like I say, 1,000 data nodes. I have 1,000 task trackers. I have 1 name node, but that's going to become 3 when HA kicks in. I've got job trackers coming out, you know, left, right, and center. I've got Flume nodes, hopefully feeding data into your system. Understanding and managing the configuration of all these machines is hard enough when these processes are distinct, but they have complex interactions. If HDFS fails, there is a cascading effect throughout the rest of your system that means that you cannot just treat it in isolation. You cannot manage it, say, through a Puppet installation that just knows about HDFS. You need tools that are understanding of the entire ecosystem. Upgrading a cluster is actually, you know, I can speak from experience at Cloudera, is one of the most difficult problems that our customers face. We get trouble tickets that come in and say, I am on, you know, a version of Cloudera's distribution for Hadoop, or I am on Apache Hadoop X, and I would like to upgrade to X+1 or Y+1, and it's not working. Or I've followed the steps and they're not working for me. And often it's user error, but that's still a problem. Managing the upgrade of a cluster, particularly as more and more clusters become productionized, is a very unglamorous, unsexy problem, but is so very important because availability is going to be key. As much as we would like, when you make changes to configurations with Hadoop systems, they're not always idempotent. It's unfortunate how many times just turning it off and turning it on again actually works with Hadoop nowadays. And this is, again, a problem because getting the system into a known ground state can be tremendously hard. I tried this reconfiguration and I brought the system up. What do I know about the system at this point? Is it working? Is it not? We need tools that mitigate just the costs of difficult configuration tweaks. I actually want to insert kind of, you know, a middle bullet point here, and my point therefore is that embedding domain knowledge into your configuration management tools is absolutely vital. Puppet, for example, and I don't mean to rail on Puppet, it's a fine tool, but it's one I'm going to use as a straw man, in fact, doesn't know itself until you program it whether it should bring down HDFS before MapReduce or the other way around, what to do with the Flume ingest while HDFS has gone down. You know, the job tracking needs restarting. What else needs restarting? What other configurations as a cascading effect do I need to take advantage of? You need to embed this knowledge into tools. The alternative, and I was talking to someone today who was struggling with this exact problem. He'd written a number of bespoke scripts to manage the upgrade of their Hadoop cluster, and they didn't work perfectly. This is not a problem that should be solved by everybody 100 times. It should be solved by software once. Ideally. Yeah. This feedback loop that I'm advocating for, but where monitoring data feeds into the management data so that the management system understands the state of the cluster and therefore what the correct series of steps to take to perform certain management actions. That feedback loop should go the other way as well. Management tools that understand, as I say, the ground truth of their system should feed into monitoring data, because otherwise interpreting that monitoring data is just tremendously hard. How do I know if this is a reasonable value for throughput of my cluster? How do I know if the utilization is an acceptable value? Until I know how the cluster is configured, I don't have any kind of frame of reference established. And therefore, I'm arguing again that management and monitoring tools are two sides of exactly the same coin, and splitting them out is not what we should be aiming to do. There's also a bunch of value to putting all of this information in just a single place. It makes it easier for users. It makes it easier for operations engineers. And it makes it easier for support people to investigate problems with your cluster if they can see both configuration ground truth and monitoring in the same place and know that they are internally consistent. Now, I have a screenshot warning coming up, and I wanted to add a caveat at the beginning of this talk. This is not a sales pitch for Cloudera's tools. It's no secret that we are building management and monitoring tools, but I have absolutely no interest in trying to sell you them right now. If you'd like to talk to me more about them, please come up after the talk. But I'm going to show you a couple of screenshots to illustrate a couple of points I'm trying to make. So I apologize that the font size is tiny for me and pretty tiny for you as well. This is a single pane of glass that we have built to monitor a single instance of a Hadoop cluster. And I hope you can see my mouse pointer. We have a list of services here. We can see, so not only their service configuration, but we can see their health here. We can see how many machines compose that service. I don't want to dwell particularly on this, but I just want to say that putting it all in one place can make it very easy to quickly understand that, hey, MapReduce doesn't seem to be working particularly well because its configuration is outdated. Moving into the second of my use cases. Cause and effect is tremendously hard to understand, but it's absolutely vital if you're to understand what happened. If you get in the morning and it turns out that all your task trackers restarted overnight, how do you actually kind of play detective and go back and piece together what happened? Currently, the answer is typically go look at the logs. Well, that's fine. There are 4,000 logs being produced in a Hadoop cluster at any one time for reasonable scales. That's kind of, most of your day gone. So the question I want to ask to start off with is, how do we know that there's something wrong in the cluster? What's the standard behavior of a cluster that we should be aiming at? And how can we tell what caused this fault if it actually, if there is something that turns out to be wrong? So why is this hard? Well, sometimes it's easy. Sometimes your cluster is on fire. The problem that you have is that your cluster is burning down. But unfortunately, that doesn't happen too often. Most of the time, you have an error, you have a task tracker restarting continuously, you have your HBase clients unable to contact their region servers, you have the region servers unable to contact the master, but you don't know why. This is made much more difficult by the fact that these are distributed systems. And distributed systems make cause and effect tremendously hard to understand. For one reason, time is not constant across machines. Time moves forward at different rates. It's hard to say that this event on this machine happened before this event on this machine. That would be the standard way of saying, event A caused event B. Hadoop itself is tremendously poor at explicitly tracing the causal relationships between events. For example, if Zookeeper enters a garbage collection port, then the HBase master may eventually may eventually time out. There's nothing built into Hadoop because these are different projects that, and I'm using Hadoop in kind of the umbrella sense to describe all these projects. There's nothing in Hadoop that says this event in Zookeeper caused this event in HBase. Yet, diagnosis is what we're trying to achieve here. It's made even harder by the fact that Hadoop is a large distributed system. It makes it very difficult to understand actually whether something is an error condition or whether it's just not ideal. Google had the great insight that I think almost kind of kicked off this whole commodity computing, commodity cluster computing revolution kind of with the MapReduce paper, which is that something is always failing. Like one of your hard drives is always going to be running suboptimally. It's not going to be running, it might have crashed, it might have lost data. That is the standard state of affairs for a large enough Hadoop cluster. In particular, this means that failure is no longer a binary event. Your web server is typically either up or it is down. It is either serving requests or it isn't. Clients are either timing out or they aren't. In Hadoop, you have degraded service. What's acceptable, what isn't, and how do you measure these things? As I say, failure generally the norm. And excuse me. This means that failure events on particular nodes are hard to understand in the context of a larger, hey, this thing is actually really broken event, and you should kind of be talking to your supplier. Or, it's fine, a task tracker is failing, but a task tracker fails every day. Don't worry too much about it. Just replace the hardware. So in the absence of causal, this thing caused this tracing, the best thing you can do is identify correlations in the software, in the cluster. In fact, I've just said that. So correlations across time are important. All of these events happened at roughly the same time in the cluster. That tends to imply that they're related somehow. But what traditional monitoring tools can't give you is domain-specific correlation. For example, all my pig jobs are failing, or the machine that the job tracker is running on started swapping, and then the job tracker started running slow, which means that the tasks aren't getting scheduled quickly enough, which means that throughput is degraded. Again, that's a long causal chain of events that's hard to identify with traditional monitoring tools. What this means, in my opinion, and what I'm positing, is that with so many disparate actors in the system, you need tools that hierarchically manage these different actors, that present them in a drill-downable way. So at the top level, this is my cluster. Underneath it, these are the services that are running on it. Underneath that, these are the processes in these services. And at the same time, as I'm demonstrating here, you also want to be able to drill down on a per-job basis. And this is a screen that we've built in Enterprise 3.5, which is the thing we've released today, no sales pitch. Whereby you can drill down from the top level job into the map-reduced jobs so this is a pig job. Underneath it, you've got map-reduced jobs that comprise it. Underneath that, you've got the attempts. This gives you kind of like, at the top level, a way to immediately see if something is wrong. Of all these jobs failing, well, I've just got one job failing here, so that's not the end of the world. But if all my pig jobs were failing, this is an easy way to visualize kind of this correlation between different types of things. I also argue that Hadoop needs core improvement in the area of kind of cause and effect determination. It's great that Zookeeper is built independently from HBase, which is built independently from HDFS. But it would be wonderful if we could actually build a system that allows us to understand when requests are moving between systems. And I suggest that it's absolutely vital, therefore, to support tracing in the RPC layer. This is something that's been posited for a while, and people read kind of the Xtrace paper and Google's Dapper paper, thought this was a really good idea. And then it kind of, efforts to do this founded slightly on the rocks of some controversy over which RPC framework should be used. At this point, I think the choice of RPC framework is kind of moot. I think what we need now is to stick with one and build into it the ability to trace RPCs across systems, and also the ability to say, this user caused this chain of events inside the system, which had this net effect. We can't do that without Hadoop's help. No matter how good the tools are, Hadoop needs to kind of come halfway and meet us. And while I'm here asking for things, I also believe that there's a great deal of value to be gained from fine-grained metrics, from excuse me, from the ability to quickly decide if a distributed lock is heavily contended, or if a subtree in Zookeeper is seeing a great deal of write throughput. These things can be key to understanding subtle performance problems, because they can, like ripples in a pond, cascade into very much larger performance problems. But he seems to have finished early. It's my understanding that capturing these sort of things can be extremely expensive. So much like dtrace, which is a system I admire greatly, let's also, while we're thinking about how we can monitor all the systems in Hadoop, build fine-grained metrics that we can capture or not capture at will. So to the third of my use cases, capacity planning. How big is my cluster? How do I know when to make my cluster bigger? When do I write a check to my very nice OEM manufacturer? Thank you. 5 minutes, okay. This is going to be quick. A better question still, how well does my cluster match my workload? Capacity planning actually shouldn't be about deciding when to make things bigger. It should be about, have I got the right size tool for the job? Again, why is this challenging with Hadoop? Well, unlike a web server, which is serving requests, that's what it does. Hadoop can see extremely heterogeneous workloads, and they can change over time. Like different departments can place different loads upon the system over time as their workloads change and evolve. But Hadoop stays constant. Multi-tenancy, which is, and I mean multi-tenancy in a slightly different context than is traditional here, both of the execution framework, so now we've got MR2 coming, which means it will be able to run many different kinds of things on a single cluster, and multi-user, so Department A and Department B both want to use Hadoop at the same time. Make the problem harder because it's yet harder to understand what the steady state usage of your Hadoop system is. And a follow-on problem is, have I bought a too big cluster, or is nobody using it sufficiently well? Are my users not actually taking full advantage of the power that I supply? So one thing I want to posit that is there's been some talk recently about what are the correct metrics to build in order to understand the capacity and utilization metrics for Hadoop. I suggest that goodput, which I'm going to define in a minute, is actually a reasonably powerful proxy for understanding whether my cluster is the right size. I define it in much the same way as networking protocols. So TCP goodput is the number of useful bytes sent compared to the number of total bytes sent in terms of network overhead. For Hadoop, I define that as the total amount of time spent doing real work compared to the amount of time the cluster spends doing work on the behalf of a particular job. So what can cause bad goodput? What can cause inefficiencies? Well, small task splits. You have far too many tasks. Each task carries with it a little bit of overhead. Misconfigured JVM reuse settings. If you're spinning up a new JVM for every task, that's extra overhead, extra time spent doing work, but not actually producing any useful output. High speculative execution rates. If you have tasks that are continually getting rescheduled on your cluster due to the scheduler saying that a certain task is slow, you're now doing almost twice the amount of work for the same amount of benefit. This is hard to measure with high accuracy, but easy to get good approximations. And once you have this good approximation to goodput, it tells you whether your cluster is actually being efficiently used or whether it's actually spending all of its time doing useless work. To the fourth of my use cases, which I'm going to cover in 2 minutes. Oops. So in the case where there are no obvious major faults, the cluster seems acceptably utilized, and yet you have a user on the phone saying, my job is running terribly slowly. How do you respond to them politely? More specifically, how can we actually test that hypothesis? Because you and I know, don't take the user's word for it. Measure. There are two possible approaches that I'm going to outline here. The first is, ideally, we have a wonderful analytical model of job execution time. I give it the description of my job. It whirs and clicks for a second and comes out with a description of how long this job should take to run. Brilliant. Unfortunately, it's a unicorn. Can't be found. Some people have made approximations to it, but they're still full of error, unfortunately. So a practical alternative. Let's use history. How slow was the job before? How has that changed over time? Then all we do is compute the distribution of historical job performance and compare the current job's performance. This only works for periodic jobs, of course. A quick rule of thumb, within one standard deviation of the mean, no significant change in performance. Tell your user to go and do something else, make a cup of coffee and wait. Anything outside of that suggests that actually the user is probably right and they have a legitimate complaint. So in order to do this, we have to create a job matching framework that says, well, is this job the same as a previous instance of this job? How do we build up this history over time? It's a difficult problem. How do we know when two jobs are the same? Hadoop could help us here by capturing more interesting metadata, but for now, we just have to kind of read the tea leaves and say, time of day, submitting user, the map class and the reduce class are the same. These jobs are probably the same. Query jobs are yet more difficult because they run often the same mapper and reducer. So you can have to do a little bit of analysis on the query string. And here's an example of how you might visualize that. So I've taken a whole bunch of sleep jobs, and I've run them, and I've run one particularly big sleep job, and it's taken much longer than all the other sleep jobs. Here's a quick way to eyeball that and say, this column here, the duration, significantly longer. I'm going to quickly run through this because I think I'm pressed for time. So if your job is really slow, what do we do? There is really one major cause of slowness that we see. There are several major causes, but this is one particular one I want to highlight, is skew. Two predominant causes of skew is environmental skew, which is when identical tasks run differently depending on where they run. So one task tracker is running tremendously slowly, and it slows the whole MR job down. MapReduce is predicated on a notion of homogeneity. If you don't have homogeneity, you get slowdown. A different kind of skew is workload skew, where supposedly identical tasks have very different amounts of work to do. Normally your partitioner is broken. How do you diagnose this? An easy way is just to throw up a heat map, which is something we've built as well. And along the bottom of this heat map, I've got the number of input records. And along the side, I've got how long the job took to run. And the cells themselves are densities, so how many tasks took this long to run. You can see here we've got a fairly noisy distribution. Tasks that are towards the left, but at the top of the heat map, are taking a very long time to run. Well, this is all relative to about 20 seconds, but bear with me for the data. And you probably want to consider changing the task tracker on which these things run. Along the bottom, if you've got tasks that are running very quickly but have a lot of data, that's fine. But in the top right, you also have a problem because you have a distribution of input sizes which is problematic. You want to, again, like I say, keep things homogeneous, keep data distributed uniformly across all machines. This is my final slide. How do we fix skew? Well, once the cause of slowness is understood, it's really easy to be remedial. You either blacklist the task tracker if it's taking far too long to execute reasonably sized jobs, or fix your partitioner because it's not partitioning work amongst the tasks uniformly. So in conclusion, and I thank you for bearing with me through a rather breakneck half hour. My basic thesis is that Hadoop clusters are uniquely challenging from an operational perspective, and tools need to help. They're not sufficient, but they are necessary. Traditional approaches are valuable. Ganglia is great. Nagios is great. Alerting systems don't change very much in the context of Hadoop. But domain knowledge is absolutely vital, as I hope these last couple of use cases have shown you. So dedicated tools are important, and so is increased support within MapReduce and all these other systems as frameworks in order to make their monitoring and their management more feasible and easier to do. And with that, I'll say thank you very much. I'll take questions because I'm the last speaker, and I presume we've got a couple minutes. Good. Thank you. Sure.
I'm just curious, how many of those tools available right now?
All of them, but they're available on a subscription basis from Cloudera.
So all of them available for subscriptions?
I believe so, yeah.
So I have a question about the abnormal behavior thing. So more often than not, I see this, that the job, we have a heterogeneous cluster with various different kind of machines with varying IOPS and all that. So at the same kind of job with a similar workload, same job with similar workload, day over day variance sometimes are more than one standard deviation apart. So what do you think? So you mentioned environmental factors where the host on which they are running is probably not good. Or so what's the best way of, what do you guys do for such kind of diagnosis? Do you look at the historic job histories and figure out like what kind of host they ran on?
So typically in a large enough cluster, and I just want to repeat your question to make sure I've got it. You're saying that there is heterogeneity across task trackers.
Right,
and,
right.
And that's fairly well established. So what kind of tools are we using to diagnose those faults?
Yeah.
Okay. So typically this only really affects intra-job performance. Different tasks from the same job will perform differently, which is a killer for performance.
Right.
So if I jump back a couple slides and show you this heat map, we'd use a visualization like this to show cells, I'm trying to find my mouse pointer, cells that are in the top left have a small amount of data but are taking a large amount of time. that typically means that that's an environmental skew.
Okay.
So what we have on the right-hand side is a table that shows the task trackers on which tasks in that cell ran. So you click that cell, up pops all the task trackers. If they've all run on one particular task tracker, boom, there's your culprit. Fire that task tracker.
Right. No, so this kind of heat map for a single instance of the job is good, but like if this could be made available over the multiple instance, if it's a periodic job, similar kind of workload, but it's like a combined heat map which you can then see to figure out.
So what would be the axes on the combined? Because I see. So you'd have like input size across the whole job.
Yes.
And then run. Yeah, you're right. That would be a very useful visualization.
Okay, thanks.
Thank you.
You have covered about where you have an issue which you can detect or see, slowness, etc. But do you have any tools where you can advance alert? Which what I mean by that is maybe a node is weak and 2 days down the line it will, it'll go down, but there is no apparent symptoms. Is there a way where you can track that ahead of time and alert that these nodes better watch out?
Yes and no. So absolutely yes, there should be tools, and I'd like to talk to you offline about some plans that we have. In the tools that I've shown today, what we have is the ability to monitor those tools. So if a human, those nodes. So if a human is watching, and we have some time series views that will very explicitly show degradation, for example, in performance. If a human notices that this degradation across the cluster, and this is the importance of hierarchical displays like I was saying, if you look at the cluster and see degradation in performance, you can then drill down to find where that degradation came from, and ahead of time, hopefully, mitigate the problem.